Welcome to another video, and specifically about transformers. With the transformer, they're all around us. They're in your television sets, they're in your computers, they're in your iPads, they're in your phones, they're in phone chargers, etc. And basically they convert one voltage into another. They either step the voltage up or they step the voltage down. Because if the voltage was too high, we would blow the circuit board. And so fundamentally, a transformer is just a device to convert voltages into different values. And it does this by the process of electromagnetic induction. In fact, transformers are a way of transforming energy from one type to another. So if we visualize a transformer like so, I mean, Michael Faraday basically made a transformer when he was investigating electromagnetic induction. He had a ring, and this one I'm just using a rectangular ring or a square ring, but he had a ring, and around that he put wires. Okay, and if you remember when we talked about Michael Faraday and his discoveries on electromagnetic induction, he noticed that a current was only induced when there was relative motion between the coil and a magnet. But in terms of his ring, and with the wires attached to it, he noticed that when he opened and closed the circuit, it was only during when it was being opened and when it was being closed that we had a generation of current in the second coil. And so he was actually making a transformer, because what's actually happening here is, here you have electrical energy, right? So you're supplying a current and that's creating a voltage. And then that electrical energy is then transformed into magnetic energy. In other words, this alternating AC current, this alternating change in flux, is creating the transfer of electric flux, of magnetic flux I should say, through the core. So we have a core here, and that is a substance through which we get magnetic energy happening in here. Right, so you're getting a transfer of this magnetic energy. So you're going from electrical energy to magnetic energy, and then this magnetic energy induces a EMF in the wire, and therefore a current. And so we're going back to electrical energy again. So this core is made of soft iron, right? Soft iron core. This here is the input, and we call this here the primary coil. And this one over here is the secondary coil. Now if we were to give some symbols to this, well, since this is electrical energy here, we're going to say that we have an initial voltage V and lowercase p to represent it, P for primary, so the voltage of the primary coil. Then of course we have the number of turns, because if you remember that when we're talking about electromagnetic induction from Faraday's law, it's dependent on the number of turns and the change in flux over the change in time. So the number of turns affects what the induced EMF is. And so the number of turns here in the primary coil, we're going to go NP. And then we have the number of turns in the secondary coil, so we'll go NS. And then of course we have the secondary voltage over here. So we have 4 coefficients that we can write symbols for: primary voltage, secondary voltage, primary number of turns, and the secondary number of turns in the coil, secondary coil. So let's talk a little bit more about transformers, and I'll just rub this bit off so we've got a bit more space. All right, here we go. We've got a very basic diagram here. So we've got a coil of wire here for our primary coil, and I've just labeled that number 1. Then we have the transformer, or the iron core, right, the core here, and we can just make it a bit thicker if we want to. Okay, and that's labeled 2, and then we have number 3 over there. So if we're to talk about the different steps of what's going on here, the first thing here is that AC current, this alternating current, causes a change in magnetic flux around the coil. Now that change in magnetic flux causes this flux to be carried through our ferromagnetic coil here, our core I should say. So let's write this down. So that alternating AC current causes a change in flux to occur around one section of the core. All right, so we have AC current there inducing a change in magnetic field. That change in magnetic field makes a change in flux, because remember, flux is just the magnetic field times the area. And so we have a local change here. Now this local change causes the change in structure of the iron core. It's a ferromagnetic material, so ferromagnetic materials are influenced by magnetic fields, and so all the domains and so forth change in orient and change in their positions, and it transfers that flux from one position to another by induction. So into here, I guess we could say that we have the transfer. Now that change in flux is passed through, and sometimes that's called flux linkage. We're linking two areas together, right? So flux linkage, we're linking the change in flux from one area to another, and we're passing that around through a ferromagnetic core. All right, so that happens through air as well. Of course, you know that we did that before, but of course, being an iron core increases the efficiency and the magnitude of the size of the flux, and so therefore it's more efficient to use an iron core than just air. So we can have air transformers, but iron core transformers are more efficient. When it gets to position 3, we then have this conversion from magnetic energy back to electrical energy by, of course, this change in flux causes an induced EMF in the wire, and that induced EMF creates a current, and then of course we have electrical energy there. So that's the basics behind our transformer, and we're going to be looking in more detail at some concepts and how we have some, I guess, problems with our transformer, because this transformer here is called an ideal transformer. An ideal transformer is where you do not have any loss of energy. Okay, and we're going to get into that as well. So what are the two different types of transformers? Well, if I was to classify them, we have step-up transformers. And as the name implies, we're going from a lower input voltage to a higher input voltage. And so if I was just to do a very basic diagram here, let's say we have two little coils there, and then we have multiple coils over here. So you can see that the number of turns in our secondary coil is more than the number of turns in the primary coil, and so therefore our voltage coming out, our secondary voltage, is a lot higher compared to the small primary voltage we've got here, right? So the primary voltage here is less than the secondary voltage, and that's a step-up transformer. And so you would get that in devices inside like the old TV sections where you want to increase the voltage across the electron gun to fire electrons towards the screen. You need a larger voltage to cause thermionic emission of the electrons in the gun. So you want that sort of transformer just there. So for example, we can do the opposite. We can make a step-down transformer. And as the name implies, the step down is doing the opposite. You start with a very high voltage and you're going to a low voltage over here. So you plug your device into the power point. In Australia it's 240 volts, but you only want 12 volts for your charger for your phone. We need a transformer to change 240 volts down to 12 volts. And so therefore the primary voltage is a lot higher compared to the secondary voltage. Okay, and you can see that's got to do with the number of coils in that as well. And we're going to get to explaining and understanding more about that when we look at the transformer equation. So hopefully that's made a little bit more sense and explained some of the fundamentals of what transformers are. Devices, they're a transforming device that goes from electrical energy to magnetic energy to electrical energy. That they are, in the ideal transformer case, we don't lose any energy, where they're 100% efficient. And we do this by electromagnetic induction. Alternating AC creates magnetic flux, which then causes induction over here. And that we have two different styles, types of transformers, step up and step down. All right, I hope that makes sense. I'll see you in the next video where we start to take these concepts of transformers into a little bit more depth.